All right, this next lecture will involve a set of videos which will show you on some of the work done at the two ACE laboratories. And then I will have a brief lecture on kinematics. And in fact, the sequence of topics which are going to show up in your rest of the course. So here is actually an inverted pendulum which is very similar to what we have in the lab, and we will have actually two versions of it, two versions of this. This is a single pendulum. You can have a double pendulum.
It's our lab.
Proposed in certain units. Yes, some certain.
So what's the controller you use right now? What's the controller you use?
Okay, let me actually let me do it. I wanted to give a comment on it.
In certain.
Okay, look at this pendulum. Remember we talked about adaptive control a few minutes ago, and we said you have a dynamic model for the system, in this case a pendulum, and if something happens to that pendulum, that plant, we change the model, the controller doesn't know it. Okay? What we did in New Mexico, and also when I was in France, we did it in a laboratory in Toulouse, we put a flat surface on the top of the pendulum, and we put a plastic bottle first, and manipulate the pendulum like that, back and forth, with something on top. When you add a mass of any sort on the pendulum, you change the center of gravity of the pendulum, the model is changed, the mass has changed, inertia has changed. So the old model is no longer valid. Some controllers may not be able to understand that. Okay, they're not robust enough to do that. Some intelligent controller can do. We put, I will show you video later on, we put a glass, we put French wine on it, and we balance it. Or we put rodents, mice, on a flat surface, wandering around like a random walk, and change the plant, and then controlling, keep them still. Okay, so you can do many things to mimic that. Let's now go to actually ACE. ACE has its own channel on YouTube. This is ACE YouTube channel. And there are plenty of things that we can look at. For example, here, I may stop some of them early, but this is actually a student, controller students of mine 2 years ago, that they did drone, they ran an image-based drone flight control system. You see, this is the lab view video, and this is students showing an image, and then the drone is going to follow. challenges, remote. Let's see. This is a group. This was a group last year in the same course.
As you can see in this project, we have a Swedish wheels, mostly in military application. So you can control the robot and make it maneuver to side. So you can work on really small locations like submarines. In case of an emergency, the robot can able to turn on and off the water valve in case of fire. So these wheels give us a
The camera.
advantage. Yeah, the camera, it has a camera in front, so it calibrates itself based on the color tags you see in bottom, pink and green. So it calibrates its heading angle. So the robot can understand, okay, I'm on just line up with the valve, so I can use the manipulator. The end effector looks like the valve, so it can turn on and off.
Here is actual one of the. This is the. Okay, here. This is the robot you're going to be working with. This is Vikram is actually using the ABB industrial robot to create the logo of the lab.
Perfect. Can you screw up to that? That's all.
It cannot pick up a brush, paint and paint those and make them into the three domains that we have: air, sea, and land. This is one of our actually underwater robots that was done several years ago. It was actually on Fox News.
That's one small splash for man and one giant leap for mankind. UTSA students and staff have developed underwater robots that can think for themselves. For those who've spent years working with robotics, it's a dream come true.
Yes, this is the ultimate. Making something that will work on its own without your assistance, but only because you've programmed it, you've told it how to work. It's a lot of fun.
These robots are equipped with navigation, sonar, cameras, sensors, and most importantly, a microprocessing system, essentially a brain that allows it to talk and work with other robots.
Suppose if there is a rock, if one finds there is a rock, you should not hit the rock. Should you communicate with the other robots? So, okay, fine, there is something ahead. So please choose your path to go somewhere. It's called distributed intelligence.
You'd be amazed at what an army of these robots can do working together without putting people in harm's way. Missions ranging from underwater inspections to border security, exploration, and even search and rescue. Let's say I was a diver stranded underwater. A swarm of robots just like this one would be able to find me and cover a lot of ground using not just cameras for visual proof, but also metal detectors to find any sort of metal items I might have with me. This type of engineering is nothing new to UTSA. Last year we showed you what students were doing with technology like this on land. This year it's water, and of course that means robotic aircraft will come in the future, something that could put UTSA above the rest.
To the best of my knowledge, no other place in the country was looking at all three domains simultaneously and connect the dots between them. This is what we hope to achieve.
Adam Kruger, Fox News at 9.
Okay, let me show you Winnie Darwin that brought a program and trying to dance that Korean dancer. What we're trying to do hopefully in this course, Berat and his team is going to use the guts of this robot and create a larger one and put it in there. Create a bigger one. This is about $500. Okay. All right.
And we have a new version of it. If you, now it's Ravdibot. It was pretty old when it was famous to Gangnam Style. We used 3D printing to, it's on there. By next to our Christmas tree, Darwin Mini regenerates as a Ravdibot. The second video on top.
We had a company here, a company in Canada contacted us a while ago, and they wanted to actually use some of our algorithm on Vision SLAM algorithm for floor cleaning robot, which would clean large spaces after the hours, after the, let's say Walmart is shut down and they close for the business, and these robots stay on the come out of the stations and come and clean aisle after aisle and so forth. Or you go to a big mall, you want to clean that. So we designed, no, this is actually not that one.
So it's a beam motion processor.
Yeah,
Double.
it's this one.
Yeah.
This is a Pioneer robot which actually moves from cleans floor and goes from one side of the aisle to another side. you will be working with this robot for experiment number 2 or number 3. And now, for example, this could be one rack of the Walmart, this is the other one, and just goes around and around and finishes the whole area. And then when it reaches, this is actually the floor of the BSE building on the campus, where what the students have done was, at that time, Patrick and now Dr. Benavides and Mohan Mopidi and some other undergraduates working, helping them. They moved a mobile robot on the entire second floor of BSE building and took pictures every few milliseconds. And they built an image database, knowledge base, or image base on the memory, on the computer, on the robot. And then they brought the robot and looked at that same area before and take a new image, and it compares it with what it already has, based on what they already had and the coordinates of where the previous image in the image base was taken, knows where it is, within some accuracy, plus or minus some tolerance. Then you know how to locate it. And then take another image furthermore on your train or on your environment, and you compare it with another image, you know where that is, then now you have two coordinates, A and B, you go from A to B. Okay? That's the algorithm that we also are patenting. The A slide is to your right. Of course, the robot, if it moves, let's say during the day, which is not the case because you want to clean it after the hours, you need to avoid obstacles, avoid people. Okay. Anyhow, we have. I think we are probably, you see, we have also put into that humanoid robot into the waist and head of a roadrunner. This is a roadrunner. The same robot, we changed it, we bought a new clothing for it, and a new hat. Courtesy of 3D printing. Oh. Okay. All right. So let me now go. Actually, this is also interesting. It's a work that was done by by
And remember those
You can
robots
skip
years
the
ago?
half.
This is the guy.
You can jump to the half, Professor.
jump to, yeah,
A little bit forward, maybe. Yeah,
no.
that's enough.
Which is a floor cleaning robot by what I call it in my dissertation, with a more friendly name of Cleanie.
One robot is being picked up by another
Actually,
one.
is paired up with another robot, which is an assistant walker. So the assistant walker also has the same type of camera, the RGBD camera, and it will be able to navigate or assist the navigation of the elderly or disabled person, the user. And in particular, I was interested in some sort of robot that could go around, say, my grandma's house. She's going to be 95 this year. She's using a walker, and many times there's something possibly in her way, the type of places she's going. Eric really enticed us to get into 3D printing, which really helped because last year, around this time, this robot itself was just a Roomba, a bolt, and a platform, and the Kinect. So we have really been able to accelerate learning. You can actually rapidly prototype your wildest ideas from your computer into a physical object the same day.
You may have seen Patrick on the website of the UTSA just before he graduated last May. Okay, so much for videos. And later on, when we have guest lectures, we will give you access to actual full-fledged set of videos, which we found on YouTube to teach you Python, to teach you Linux, or to teach you Hadoop, or MapReduce, and other elements of cloud computing, or robot operating system. So you will get live lectures here, but you also get those links and you can watch those. And with the combination of those two, hopefully you can really get something. And some of the projects, perhaps all of them, would require some knowledge of ROS in them. So it's by design what we are doing for you that is going to help you with that. So let me now go to a kinematic, another set of slides. In this slide, you can see basic elements of manipulated robotics. On the top, you see kinematics, which, as you will see, is the motion of one link with respect to another link without the consideration of the source of that movement. You get plenty of information about kinematics, forward kinematics, inverse kinematics, and so forth. Dynamics is essentially a modeling of the robot. And it's highly nonlinear, and highly interactive, interconnected, I should say. If you look at the industrial robot like the ABB, it's 6 degrees of freedom, from base to shoulder to elbow and to wrist, which has 3 different motions: pitch, yaw, and roll. Pitch, yaw, and roll. So you have 6 degrees of freedom, and that is determined enough to work in three-dimensional space. If you see a robot who is doing, let's say, a smelting or painting or something, Right here in San Antonio, you can go to Toyota factory of Toyota company, and you can see robots everywhere. Okay, and those are working in a cell, which is slightly larger than the workspace of the robot. And material comes, or a belt comes, bring a piece of that engine, and robots work on it and goes on. Some other robots trained to do different things, later on work on it some other way. Kinematics and inverse kinematics, as you will see, and are part of the foundation of programming the robot to do things repeatedly, time after time after time. So robots are good and bad. They're bad because they may put some humans out of work. They're good because they don't strike, they don't get tired, they don't do anything. Okay, they don't make mistakes by and large. Then task planning. Task planning is the way you are moving. If you look at a 6 degree of freedom robot, just like what I told you previously on a 11-piece snake robot, each of them are one control system. On this one, you have 6 control systems. One moves the base, one moves the shoulder, one moves the elbow, and so forth and so on. So you have 6 control systems simultaneously have to be controlled. That's what manipulated robots is all about. That means you have 6 inputs into those 6 control systems. And they're all time varying because you're moving in 3D space. It's not like going this way, that way, like that. Okay? Those are for Walt Disney cartoons or something. So what you then need to do is to, based on the input of every joint of the robot, come up with the right control mechanism to smoothly move it from place to place. And once it touches a piece of the engine of an automobile, it's now in what we call Cartesian space. It has to have touch sensors, feeling sensors, it has a force sensor, it cannot damage anything. So all of that has to be figured out. That's why sensing is important, kinematics is important, dynamics is important, control important, and of course, artificial intelligence if you wanted to do something more sophisticated. And software is a big deal of it, sensor, control, hardware, mechanical design, actuator. All of those are elements of a typical manipulated robot system. 20 years ago, that was the only robot system we had. Now we have many. Controlling a quadcopter or unmanned aerial vehicle or a drone, that's huge. It's highly nonlinear model. So, in order to control and program a robot, we must have knowledge of both its spatial arrangement and a means of reference to the environment. Every joint of the robot has to know where it is with respect to a reference point, an XYZ origin, okay, where we call it 0 or kinematics is the analytical study of the geometry of motion of a robot arm with respect to a fixed reference coordinate system, or without regard to the force or moments that cause the motion. So this is typical definition. Of course, all of these are on your Dropbox, by the way, and hopefully you have downloaded them for your own personal computer. Here is a task. We have a camera here. The camera wants to tell this robot to pick up this ball from here. Okay. So here's your right-hand coordinate frame. Your frame is here, right here, here, and here. And this base is somewhere away from that. There's a coordinate here, there's a coordinate here, there are 3 coordinates here. Link frame, tool frame. The end effector is your tool, whether it's a paint brush or something like a screwdriver or soldering gun or what have you. And this is the goal. This is where you want to go. So the robot needs to be programmed in such a way that only comes and picks this up. Okay? When you move to a location, you have 6 motions, one come after another. Then you know at the end where you are in the free space. But unfortunately, 99% of the time, you don't have the luxury to wherever you want to go. You have to go to a specific place because you're doing a task. You're doing a useful work. So that's where the inverse kinematics come into the picture. Having a goal like this, a specific XY coordinate of this red ball, how much each of those 6 joints have to move to get there exactly. That's the inverse kinematic problem. Okay? And that has a problem which has an infinite solution. You'll see later. But you have to choose the right one. So camera has its own frame, and then you go there and you actually choose that. Between 2 frames, we have a kinematic relationship, basically a translation of and a rotation. If you want to go from one point to another, you have some translation and you have some rotation. You move here and then you move this way. You move like that and then you go like that. The rotation and the translation. Okay. This relationship is mathematically represented by a 4x4, what we call homogeneous transformation matrix. And it looks like this. This is your translation part. The top 3 elements of the 4th column, delta x, delta y, delta z, the incremental of where the position of your end effector or your next joint is. And then here you have a rotation matrix, 3x3 rotation matrix. Okay. So far this runs for 3x4 portion of the matrix. The bottom of it, you have perspective and you have a global scale. 99% of time this last row is 0, 0, 0, 1 because you don't want to actually enlarge the behavior of the robot to do something which you haven't already programmed. This is a lot of times come through image processing, this part of the image processing as a sensor. So this is a typical homogeneous transformation matrix. And on the robotic toolbox of Professor Cork in Australia, which we are using his textbook and his software, you'll be able to go within a MATLAB environment and build all these transformations and mimic a forward kinematics problem, mimic an inverse kinematic problem, and later on trajectory planning, task planning, moving from one point to get to the end, or control, and so forth. Using kinematic to describe the special configuration of robot given as 2 approaches. Forward kinematics is given the joint angles for the robot, what is the orientation and position of the end effector. So here I am, I go 1, and then I do this, I go like this, and I go this, that's where I am. That's forward kinematic. Okay. Inverse kinematic, given a location in the free space, which is not by your choice, but it's given to you for the task, how much each of these have to change to get there. Okay? That's the tougher problem. Inverse kinematic. Given a desired end effector position, what are the joint angles to achieve this? Okay? This cartoon here showed piece of the cake. Piece of cake like this, not so much. Okay. So inverse kinematic is the most difficult problem to solve, as I mentioned. Robot controller must solve a set of nonlinear simultaneous equations in order for the control to know, because remember I told you I have 6 control systems, 6 inputs. Each instant of time, there's the location that the end effector has to go there. Okay. That's what the numerical machine is doing. Numerical machine has an input which gives you a piece of something to carve out. Okay? And then this architecture, this piece of material is going to be digitally given to the numerical control machine, and the blade at the end of the machine, NC machine, moves exactly the way it's supposed to and produces prototype for you. Okay. Of course, 3D printer make that job much easier, than basically using it in real world. And 3D printing basically gives you a cheap way to do prototype. The robot controller must solve that nonlinear set of equations which accompanies the inverse kinematic problem. The problem can be summarized as existence of multiple solutions, the possible of non-existence of a solution, which we call them singularities. Because of that redundancy and singularity of an inverse kinematic problem, as you will see, you have 12 nonlinear algebraic equations full of sines and cosines and so forth. And you have only 6 unknown. You have 12 equations and 6 unknown. How many solutions do you have? Infinite. Some of them would be just unfeasible. It's not even in the workspace of the robot. Okay? Imagine that you have an arm and you want to work like this. No, that is impossible. You're going to break your arm. So that is singularity. So multiple solutions are possible. For example, you could pick up this ball this way, or you could do it this way. Those 2 are valid solutions. The rest may not even be. For example, you have a non-existing solution. This goal is outside the workspace of the robot. You can never do that. You cannot reach it. Okay? Has no solution. An unreachable point can also be within the workspace of the manipulator, like physical constraint. You are dealing with mechanical components which are moving all the time. Okay? And in the old days, we had hydraulic robots, oiled for actuation. Okay? Which was built in companies out of Cincinnati, Ohio, and other places. And it was gigantic robots which have to work with pressurized oil. Okay? And the problem is quite challenging. Once you solve the kinematics, you are ready for control. It's the first step for robot control. Because kinematic allows you to do Cartesian space. Then you have joint space, actuated space. This is the motor on your joint. This is the controlling the joint, in this case, angular rotation. Then you go to the Cartesian space. So you have kinematics. Dynamics is going to be the model of the system, which you will see using techniques like Euler-Newton and other Lagrange-Newton dynamics. You will see them later on. And then finally, you find a way to control the system. It may be that because you have highly nonlinear environment, you have to linearize the model of the robot to be linearized around its own workspace, to be approximately acting linearly. Do your design in the linear model, then but go back and apply it to the actual robot in a nonlinear situation. You can actually do that on MATLAB as a homework later on for the inverted pendulum before you do the experiment in the lab. We'll give you the theory in the class, give you homework to do it on the computer, and then we take you to the lab to do it in real. Okay? In 3 different stages. Joint trajectory. The robot needs to move from A to B through a trajectory, and you need to create a time history of position, velocity, and acceleration for every single joint. Okay? Trajectories are computed at runtime and updated at certain rates. And for example, if you have to go from point A to point B, you have 2 ways to do it. You can go this way, or you can go that way. That's your trajectory. Okay. Choice of 2 trajectories may wish to specify a via point, meaning, for example, you go first to this point, and then from this point you go here. Because a lot of times you don't want to jerk the robot to move very fast in an environment. You go slowly. You go to a point, and then you go to another point, and then you go to the goal. So you need to describe a path between some initial time 0 and final time of a trajectory for the robot, and then you will do it 2 different ways. We're going from 0 to TF. You can go it that way, but that's not a good one. The third one is not a good one. You don't want the robot to go more than it has to. Overshoot is not a good idea. Undershoot may also be. So you have lots of choices. This is called cubic polynomial spline. I will go over that next time. Let's see. We're going to. I think I'm going to go finish this because it's better to do that. Let me do this. I don't have only 4 more slides. You write a polynomial equation here like theta t for a trajectory of a joint angle. You take derivative of that, and because you know that the joint from going anywhere to a waypoint from another waypoint, it has to reach there, so that the angle coming in has to be the same angle going out. And it also has to end up with 0 velocity at the end. Otherwise, you're going to break something. Okay? So all of those conditions are all here. Okay? And then based on those conditions, you can compute A1, A2, and A1, A1, A0, A1, and A2 by writing this exercise. You can look at it at your leisure time, how these values are obtained. Very, very simple, really. It's a curve-fitting situation. You just get n condition of one piece of trajectory, match it with the initial condition of the next piece, and so forth and so on. So going from A to a waypoint A, then you go to waypoint A1 or A2. From there, you go to the final destination. So you have got this long trajectory divided into 4 pieces, and you have to find the polynomial coefficient for each piece of that. The nice thing about it is that when you get a robot like ABB, this is already built in. You don't have to worry about that. But you need to know how to do it in a homework type or in an exam type or what have you. So it's additional probability length. So again, you have kinematics, dynamics, and control. That's it. So this is the end of the lecture for today. Again, please start reading some of the appendices, review some of the appendices of the course book. It's written on your syllabus, what to do. And because you need to have some background in linear algebra to learn those matrices, you need to know a bit of calculus, refresh yourself in those appendices and so on. Okay, Virat will give you the not about